Okay, so in this lecture, so we're now on lecture 3 out of 4 in this series, we look at numerical solutions of the SIR model. And we also look at some final concepts in mathematical epidemiology, and this will be the idea of late stage burnout, and then also the herd immunity threshold. So we start by looking first of all at numerical solutions. But actually, I want us to start at an earlier point even. I want us, first of all, to take a step further back and to look at the 3-equation model, again, the full SIR model. So here in this little section, what I'm trying to do is to try to make sense of the fixed point U star, which is the root of f of U star equals 0, and this is in the reduced SIR model, which we were able to write as du by d tau equals f of U. Now, U star is the equilibrium solution of the reduced model, so it also has to be the equilibrium solution of the full 3-equation model. In other words, the 3-equation model with ds by dt equals 0, di by dt equals 0, and dr by dt equals 0. So I'm just going to denote r star by gamma u star over beta times n. So remember, u was the scaled version of r, so I'm just reconstructing r from u. So it's scaling. And I guess the notation is unfortunate. In this context, R is denoting recovered. It's the recovered population. R star is the recovered population at equilibrium. It has nothing to do with R naught, which is the parameter which governs whether the outbreak goes epidemic. I suppose whether the outbreak reaches epidemic proportions. So that's where the cliche comes from. Okay. So that's the equilibrium value of the recovered population, R star. I also want to look at the equilibrium value of the susceptible population, S star. So here we must have ds by dt equals 0, but ds by dt is minus beta over n I times s now with the starred values at equilibrium. And di by dt has to be 0 at equilibrium. So this is beta over n is minus gamma I, and we take the starred values. And dr by dt is 0, but dr by dt is gamma times I. So with the starred value here. So clearly from this last equation, we need I star equals 0. That's the only way you'll get equilibrium. We know that R star has to be the scaled version of U star. U star you get from the fixed point analysis. And S plus I plus R has to sum to N. So S star is N minus R star. So this is the equilibrium of the full 3-equation model. Okay. So I just getting away from equilibrium for a while, looking at the time-dependent case, I want to show you how to construct the general solution S, I, and R from U. So remember, starting with the 1-equation scale version and then reconstructing the full model. And we're going to look at everything scaled by the initial susceptible population, just in this lecture. So S over S naught from previous calculations, this is just e to the minus u. I also want to look at R over S naught. So R is U and then rescaled by the scale factor gamma over beta times n. So R over S naught will be gamma over beta times n divided by S naught. And I immediately identify this group as 1 over R naught. So R over S naught, and again, just please be careful here. S naught is the initial population, but R naught is the epidemic parameter. Just be careful. It should be clear from the context what's going on here. I have to admit, though, the choice of notation is a bit unfortunate. So anyway, this is R over S naught. And we have S over S naught. So lastly, I just want to look at I over S naught. And I just use conservation. So S plus I plus R sums to N. So I over S naught is N over S naught minus S over S naught minus R over S naught. So n over S naught is exactly our parameter A. So I over S naught is A minus e to the minus U minus 1 over R naught times U. So in summary, we can reconstruct the three equation model, and I call it the scaled model because I scale everything by S naught. We can reconstruct the three equation SIR model from the reduced one equation model, 2A, which we would solve numerically. So once the one equation model is solved numerically, once 2A is solved numerically, I reconstruct using these calculations that we've just gone through. So using 2B. So for instance, 2A can be solved. I show you how to do it here in MATLAB with ODE 4.5. So I solved the one equation model. And here is how I code up the one equation model. And then when I'm done solving, I reconstruct the three equation model. And I'm a bit of a dinosaur, so I'm still using MATLAB, but you can of course do this in some other programming language as well, for instance, Python or R. Let me show you some results. So I'm going to look at two sets of results. In both cases, A, n over S naught I take to be 10 over 9. So S naught over n will be 9 over 10. And the number of infected people at time 0 is 0. So the number of infectious people, if you like, the proportion of infectious people at time 0 will be 10%. And then I look at two scenarios. So in the first scenario, I take R naught to be 0.9. And I solve my one equation model and I reconstruct S, I, and R. And here I say that the outbreak dies out from the get-go. So the number of infectious people just goes monotonically to 0. So the outbreak is dying down. Whereas in case 2, I look at R naught equals 2. And what happens to the proportion of infectious people, it initially rises to a peak before going down to 0. And as the number of, well, all of these people from the infectious compartment, they end up in the recovered compartment eventually. So this rises cumulatively to a final value. So this is the proportion of people in the recovered class. So another approach, and yeah, before we look at the other approach, just to say this should highlight clearly now the difference between this threshold value of R naught equals 1, if it wasn't clear from lecture 2. So below the threshold, the number of infectious people goes down to 0 from the get-go, whereas above threshold, a genuine epidemic, the number of infectious people climbs to a peak before declining to 0. So another numerical method would be to solve the full three equation model directly. And I think this is, in future, if you're looking at more complicated systems of equations, more complicated disease outbreak models, a 10 equation model or something, you really need to be able to do it in this second method. And the model code for solving the full three equation model directly is given in the lecture notes. And yes, this kind of approach will be looked at in the main projects when we get to those. Okay, some nice final key concepts that we can get out from this SIR model. The first one, late stage burnout. So from the figures that I showed you, as time goes to infinity, the number of recovered people goes to R infinity, and this is strictly less than n. So not everybody gets infected by the disease. Yeah, not everyone gets infected by the disease, So R infinity is strictly less than n. And you can see this maybe more convincingly from the simulation results. So the number of susceptible people as time goes to infinity, look, it remains here at 0.2. So even at the end of the outbreak, you've got 20% of the population who didn't get infected. That's at a high value of R naught. Up here in the first case where R naught was 0.9, by the end of the outbreak, you've got 70% of the population who don't get the disease and remain susceptible. So the epidemic goes through the population, but it doesn't catch everyone. And so if it doesn't catch everyone, by the end, there'll be people who are not in the recovered class. So the number of recovered people will be strictly less than the total population size. And the fact that R infinity is not equal to n is, I call it anyway, late stage burnout. The idea is that the epidemic burns out before it can infect everyone. And we can actually calculate R infinity, and I do it numerically, as a function of the reproduction number. Or maybe the basic reproduction number, R naught. So we calculate R infinity as a function of the basic reproduction number numerically. And I've done it here, and it makes sense. As R naught cranks up, so as the epidemic is stronger somehow, as it rips through more of the population, you get more and more people in the susceptible class getting the disease and ultimately ending up in the recovered class or compartment. So eventually, for very high values of R naught and at very late times, you get 100% of people getting the disease and therefore recovering, entering the third and final compartment in the model. So that's this idea of late stage burnout. Lastly, let me tell you the idea about herd immunity threshold. So let's suppose that there actually is a vaccine for this disease. The aim, of course, from the public health point of view, will be to vaccinate the susceptible population. But if you're interested only in preventing an epidemic, in other words, from preventing the outbreak from getting this nasty peak, it suffices just to vaccinate a fraction of the susceptible population. You don't have to vaccinate everyone to stop an epidemic. You vaccinate a fraction F. And to work out what F is, let's have a look at the following. So we're going to look at things at time 0. So we're going to look at initial conditions, and we're going to suppose that there's a patient 0 who introduces the disease, but we've vaccinated a fraction F of the total population. So the number of susceptible people, the pool, if you like, of susceptible people at time 0 is the total population minus patient 0 minus the vaccinated people who we've now taken out of the susceptible pool by virtue of vaccination. So we remove the fraction of the population vaccinated from the susceptible pool. And that means that the value of R naught is reduced in the model to a new value, R effective. So let's have a look at what R effective is. So with no vaccination, R naught is just from what we had in lecture 2, beta over gamma times S naught over N. And S naught is N minus 1. No vaccination. But N is large, so R naught is very well approximated just by beta over gamma. Now with vaccination, the calculation is the same. The disease model is the same, but R effective now is S naught, which is now reduced because we've taken a whole bunch of people out of the susceptible class by vaccination. And again, N is very large, so R effective is well approximated by beta over gamma times 1 minus F. And beta over gamma is R naught, the basic reproduction number. And I guess it's called basic because it's just what happens if you don't do anything with the disease or with your population. It's somehow, if you like, the value of the reproduction number in the wild. So this is the basic reproduction number. So R effective is the basic reproduction number times 1 minus F. So again, now we want to prevent the disease, the outbreak from becoming an epidemic, from reaching epidemic proportions. So we require the reproduction number for the problem to be less than 1. The reproduction number is now R effective. So to stop the disease turning epidemic, we need R naught into 1 minus F less than 1. And so we require F to be less than 1 minus 1 over R naught. And yeah, you'll see this in descriptions online about epidemic modeling, that this is the herd immunity threshold. So now from the simple SIR model, we've seen the derivation, and it really is quite nice. Okay, so we're nearly through this series. In the last lecture, we'll look at applying these models to some data.